All right, we're going to start section 2.2 now, which is organizing quantitative data. In section 2.1, we looked at organizing qualitative data. And so a definition there, it says that a histogram, which is generally used for a quantitative variable, is a bar graph with the additional features. So the bars have an equal width and always touch each other. And the width of each bar represents an interval of numbers rather than a category. So that's important with a quantitative variable. As an example, okay, problem 4, an experiment was conducted in which 2 fair dice were thrown 130 times. Each time the dice were thrown, the sum of the numbers showing on the dice was recorded. A frequency distribution of the results is shown below. Okay, so there's our distribution. Of course, rolling a 1 is not possible if you have 2 dice, right? Rolling a 12 is the max value that you can get. Does the outcome of the dice represent a discrete variable or a continuous variable? Okay, so you're going to have a discrete variable, right? Because you're going to only have counting number values on the sum of the dice, right? Like you can't roll a 5.73, okay? You roll a 5 or a 6, right? So this would be a discrete variable since you just count up the values there. Okay. Part B, what was the most frequent outcome, and why do you think this outcome was most likely to occur? Okay, well, from the chart here, it looks like a 7 is most likely to occur. That's because there are more ways to obtain a 7 than there are any other outcome. Okay, when you roll a 7, you can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. Okay, so there are 6 ways that you can roll a 7. That is more than any other outcome on the pair of dice. Part C, and by the way, you know, as you work your way towards the center, the outcomes are more likely to occur. Okay, like when you roll a 2, there's only one way to roll a 2 on a pair of dice. That's if both the dice show a 1. Okay, if you roll a 12, there's only one way to roll a 12 on a pair of dice. That's if both the dice show a 6. Okay, but if you work your way towards the center, like these outcomes are more likely to occur. Rolling a 7, a 6, an 8, a 5, a 9, okay, that's more likely to occur. So this information really isn't surprising to us, you know, and that's what we expected. Part C, determine the percentage of the time that an 8 was observed. Okay, so an 8 was observed 19 times out of the 130 times that we threw the dice. Okay, so if we divide 19 divided by 130 gives us roughly 1.46. Okay, if we go nearest 3 digits on that. Okay, and so if I just check that here, this is what I'm getting. Now, notice how this is an infinite decimal. Okay, so if we round to the nearest 10th position, 14.6% roughly is what we get. Now, the approximation sign is a necessary symbol for whenever you're rounding. Okay, so it's not 0.146, and then it just stops. Right, it's 0.14615384662. Okay, and it keeps going. So be good about using that symbol. Okay, we're going to use this symbol a lot in this course. Okay. Part D is where they want us to construct a frequency histogram for the data. Include the height of each bar and then label both axes. Okay. Well, let's see here. So I've got my outcomes of the dice. That's given to me in the distribution. So I roll a 2, roll a 3, roll a 4. Okay. All the way up to rolling a 12. And then I'm creating a frequency histogram, right? Now the largest frequency that's listed here is 23. So I'm going to need a scale that's going to include at least 23 in it, Okay, and what I decided was to begin the scale at 0 and go up to 25 using an increment of 5. Okay, so my axes are both labeled, my number lines look good, and I'm ready to draw the histogram. Okay, and remember that a histogram, the bars touch each other. Okay, so I would just draw a bar at a height according to the outcome of the dice. Okay, so 5 times I rolled a 2. Okay, 7 times I rolled a 3. 10 times I rolled a 4. Okay, 16 times I rolled a 5. And I would do this, until I get to it rolling a 12. Okay. Now the shape of the histogram is something that's going to be important to us. We're going to do more of this kind of in this section, and then it's going to kind of go away for a little bit. But so one of the things that is important to us is a bell-shaped histogram. Okay, so notice how if I were to draw an outline of the tips of the bars here, I'd have roughly a bell curve. Okay, well that shouldn't be surprising to me because we've already said that rolling a 7, a 6, an 8, a 5, and 9, that's more likely to occur than any of these other outcomes. Okay, so I should expect to have a bump in the graph near the center. Okay, and that's exactly what happened. We're going to do a lot of things with bell-shaped histograms. Okay, so be prepared for that. Okay. Here's another example. So a definition: when a data set consists of a large number of discrete data values, or when a data set consists of continuous data, then the categories of data are created using intervals of numbers that are called classes. A lower class limit is the smallest value in a class, an upper class limit is the largest value in a class, and the class width is something that we care about. That's the difference between consecutive lower class limits. Okay, so here's an example of that. Problem 5. We have all heard of the Old Faithful Geyser in Yellowstone National Park. Okay, however, there's another less famous Old Faithful Geyser in Calistoga, California. The following data represent the length of eruption, which is in seconds, for a random sample of eruptions of the California Old Faithful. Okay, so here's my data set. Part A, does the length of an eruption represent a discrete variable or a continuous variable? Well, I'm going to have a continuous variable. Now, you don't just want to look at the numbers that are in the data set and say, oh, well, you didn't have any fractions or decimals. Well, that's okay. You can still have a fraction of time for an eruption for the length of an eruption, right? Like it could happen that maybe this geyser goes for 98.7372 seconds. Okay, so that would be a continuous variable, right? So there's no way to count up the values. Part B, construct a frequency distribution and a relative frequency distribution for the data. Let the first class have a lower class limit of 90, and we use a class width of 5. Okay, that's because the smallest value that's listed here is 90. Okay, which is why I'm starting at 90. Write each relative frequency as a decimal. Okay, so I've got my seconds, my frequency column, my relative frequency column. I'm starting at 90. Okay, and I'm using width of 5. Because I'm using width of 5, I want to go 90 to 94. Why is that? Why don't I go 90 to 95? Well, it's because of what we mean by a class width. The class width is the difference between consecutive lower class limits. Okay, so because I'm using width of 5, I need the next class to begin at 95, because 95 minus 90 is 5. Okay, it's a bit quirky how we define a class width there, but make sure you're good with that. Okay, so I go 95 to 99, and then 100 to 104, okay, etc. And then I want to get the frequencies. Okay, so I just count up the number of times that I see an eruption time that is something that is in the range of 90 to 94. Okay, and there's 1, 2, 3, 4. Okay, so I rate a frequency of 4. Okay, and then I move on to the next class, 95 to 99. Okay, so there's 1, 2, 3. Okay, and then I keep going. So 100 to 104, there would be 17 numbers listed in the data set, etc. Now, if you were to count all the numbers that are listed in the data set, you should get 44 total. Okay, and I've got a note here. Why is it a good idea to add up all the frequencies? Why add them up? Well, because I see more than I should where a student, forgets one or more, okay, and they end up getting like 43 or 45 or something like that, and then there goes the whole problem, right off the bat. So in general, it's a good idea to add up, the frequencies and make sure that you got the total that's in the data set. Okay, so there's 44 different eruption times listed, so I should make sure that I've got 44 as my total here. The relative frequency is where I need to take the frequency divided by the total. Okay, so let's see, I take 4 divided by 44, and let's see here, 4 divided by 44. Now, notice how I've got an infinite decimal, okay, and they want us to write each relative frequency as a decimal. Okay, so I'm going to have to round here. I'm calling this point to 0.91. Okay, I'm rounding to 3 digits. So now the next one, take 3 divided by 44. Okay, so 3 divided by 44. And I'm going to have to round again. Okay, so there's 0.068. Okay, and then 17 divided by 44. Okay. 0.386. Okay, so it turns out that I'm going to have to round all but one of these here. So 11 over 44 is 1/4. 1/4 is the same as 0.25. And if I add up the numbers that are in the relative frequency column, I get exactly 1. Okay, now what if we're getting like 0.999 or 1.01 or something like that? Is there necessarily a mistake? No. There's not necessarily a mistake because of the rounding error that could happen. Okay, so be aware of that. Now would be a mistake if I were to call this 0.090 and then add them up and get 0.999. Okay, that would be a mistake. So basically what I'm saying is make sure that you've rounded correctly the relative frequencies if there's any rounding. Okay, and then you might not get exactly 1 because of the rounding error. However, it should be very, very close to 1. Okay, it should be 0.999 or 1.01 or something like that. Okay, if it's not 1. Okay. Part C is where we want to construct a frequency histogram and a relative frequency histogram for the data. Okay, and we're going to let the lower class limits be the values on the horizontal axis. In general, that's going to be true. Include the height of each bar and label both axes. Okay, so I've got a frequency histogram and then a relative frequency histogram that we're going to make. So I need the lower class limits. Now those are all the values on the left side of each class. So I need 90, 95, 100, 105. Okay, and I've got that listed. And I keep going until I get to 125. Now 125 would be where the next class begins. I don't have a class that starts at 125, okay, but that would be where the next one begins. And so this last bar here is where I'm including everything in the 120 to 124 range, not 125. Okay, so the next number is just where the next bar begins. Okay, so I've got my lower class limits written, and then I label the axes. So this is length of an eruption, which is in seconds, and then the frequencies. Okay. Now the largest frequency that I have is 17. Okay, so I need a scale that's going to include at least 17 in it. And so what I decided here was to begin this axis at 0 and go to 20 using an increment of 5. Okay, and now you'll see this break in the graph on several of the graphs. All that means is that I'm not starting the axis at 0, where I normally start, but I'm starting at some other number, like 90. So I don't want the histogram to look silly. Okay, like if I were to start at 0, the histogram would be way over here, not even on the video. Okay, so that's all we mean by the break in the graph. Now there could be two breaks. Okay, there could be a break on the horizontal axis and a break on the vertical axis. Okay, whenever you're not starting at 0, use a break in the graph. Okay. So my axes are both labeled, the number lines look good, and I'm ready to draw my bars. Okay, and I'm drawing a histogram, so the bars have to touch. In the first group, in the 90 to 94 range, I got a frequency of 4. Okay, so I draw a bar at a height of 4. In the 95 to 99 range, I have a bar at a height of 3. Okay, in the 100 to 104 range, I get a bar at a height of 17, etc. Okay. And then I will draw the relative frequency histogram. Okay, now the horizontal axis will remain the same, okay, as it was over here. And the vertical axis is going to be different. It's going to be including relative frequencies now. So now from my distribution, I need a relative frequency that's going to include at least 0.386 in it. Okay, so what I decided here was to start the axis at 0 and go up to 0.4 using an increment of 0.1. Okay, and then I draw each bar at a height according to the relative frequency. So in the 90 to 94 group, I need a bar at a height of 0.091. In the 95 to 99 group, I need a bar at a height of 0.068. Okay, in the 100 to 104 group, I need a bar at a height of 0.386, etc. I still want to make sure I'm ending at 125 because, again, that's where the next bar would begin. So this last bar ends at 124, okay, which is what I have here. Okay? Now, observe the distribution shapes for the variable that are mentioned on the next page and then classify the shape of the distribution in question 5. Okay, when we hold off on doing that until the next video, and we'll go ahead and stop this one right here.